Yeah, I think my question is for Dennis. To what extent did you see systems engineering contributions to the success of COBE? And then the second question I have is, over the years, and probably that's to John, scientists or PIs are coming close to refining requirements, at least to help the engineering teams, even though they have to have this kind of spectrum to dream around in terms of what they are looking out for.
System engineering, I totally agree with system engineering. If you don't have system engineering, you're just building subsystems and pieces, and you don't know what it is you put together. And I think what we did is, as I pointed out, we brought in the 3 best engineers we could find that did system engineering from a global perspective on COBE. One of them analyzed every electrical circuit on those instruments and on that spacecraft. One of them reviewed all the analysis mechanically and thermally on the entire program. And one reviewed the entire Delta launch vehicle. So the system engineering, it was end to end. It was the instruments, the spacecraft, and the launch vehicle. Now below that, there were systems engineers working on all of the instruments and the spacecraft subsystems, and they did their piece. But we brought in 3 people who had all the experience to look at the whole system. So we couldn't have done it unless we had, we would not have been able to get up at the end and say this was done until those 3 system engineers said we didn't forget anything.
Okay, let me add a little bit about systems engineering, which is that the systems engineers that I worked with are the ones who are sort of closest to speaking as scientists to engineers. My systems engineering partners were the ones who knew how to take what I said and turn it into engineering terms. So I didn't have to do it all by myself. I thought I learned a little bit about systems engineering, but I know that I don't know nearly enough to be a real one. So you had another question, though.
About requirements.
Oh, about requirements and how do we turn them into numbers nowadays? Well, these days we have a lot better ability to simulate things in computers before we build them. So nowadays we also can predict and simulate what the sky is like. So we can simulate the first stars and the first galaxies, and we have some idea of what we're looking for a lot better than we did 30 years ago. So that helps a lot too in trying to get to real numbers for requirements.
I would also say when John or any scientist on any program comes up with what their requirements are, the engineers can sit down and work with them and have those requirements filtered down to each subsystem. They don't have to do it all on their own.
Let me also add that we end up always being driven by money. That the scientist says, I want this, and the budget people say, we can afford this. So the scientist has to say, well, okay, that is good enough for my problem, or not. And so if it is good enough, then that's what we build, because who wants to spend more money?
I'll give you an example. On John's instrument, on COBE, say 7 months before launch, something like that. Engineers love to find new things, and it's better than what we had. So somebody came in on a configuration control request to change a circuit on John's instrument. And my answer was no. First of all, we don't have 2 more weeks to do it. It wasn't the money as much, but to spend 2 more weeks to develop a better circuit for John's instrument, even though in the end it won the Nobel Prize. So I said no, and I actually got up and walked out of the room. But there was mumbling about what does he know? But the next day, so they all left. The next day, they came back with another idea they could do in 3 days. The idea was just to say no, and it contained the problem, and they put it back, and then they came back within 24 hours. Here's what we can do in 3 days, and it's better. And the answer then was yes. It's just iterations and trade-offs.